In section 1.3, we saw problems involving stretches and reflections, but we didn't concern ourselves with the order in which they were applied. Well, as it turns out, it didn't really matter. However, once we start mixing stretches and reflections with translations, the order will become relevant. Let's consider a radical function with its endpoint at -4 and -1. Suppose we wanted to stretch this graph horizontally, which is to say about the y-axis, by a factor of 1/2, and that we also wanted to reflect it over the y-axis. Let's see what happens if we apply the horizontal stretch first. Here, we will multiply each x-coordinate by 1/2. The -4 becomes a -2. The -3 becomes a -1.5. And the y-intercept remains invariant because half of 0 is still 0. Notice in all cases the y-coordinate was not affected. To apply a horizontal reflection, we simply multiply our x-coordinates by -1. This makes negative values become positive and positive values becomes negative, but does not change the value of 0. In terms of the equation, a horizontal stretch by a factor of 1/2 means replacing x with 2x. Notice in the equation of y equals the square root of x plus 4 minus 1, we've replaced the x with 2x. To represent the horizontal reflection, or reflection in the y-axis, we replace x with -x, so our 2x term becomes negative. Notice we did not introduce any brackets at this time. However, we may now factor out the -2 from the binomial expression under the square root sign and get y equals the square root of -2 times x minus 2 minus 1. So what would happen if we had applied the reflection first? Would it be any different? As a first step, we'll multiply all the x-coordinates by -1. Remember, we're going back to our original graph, which went from the endpoint of -4 and -1. Here we see the same behavior with different points. We will now apply the horizontal stretch to our reflected graph. We multiply each x-coordinate by 1/2. In the end, we see that the graph looks the same in both cases. Now let's try the equation. As a first step, we replace x with -x. And then in a second step, we replace x with 2x. So the -x becomes -2x. We could again optionally simplify this, but I think at this point we can see that both of these graphs are the same regardless of the order of the two transformations. Now this is because both of our transformations were stretches and reflections. No translation was involved. More on that later. We've begun to explore the idea of whether the order matters when applying transformations to a graph. Here, we'll see a parabola that we will stretch vertically and translate horizontally. In our first step, we will take f of x equals x minus 1 squared minus 4, the parabola on the right with the vertex at 1 and -4. And we will graph g of x, which is the transformed graph after a vertical stretch by a factor of 2 and a horizontal translation of 4 units left. Remember that a vertical stretch, in this case by a factor of 2, multiplies each y-coordinate while not affecting the x-coordinates. So the point of 1 and -4 became 1 and -8. The invariant points were the points with a height of 0, because doubling 0 has no effect. Now we will translate these points 4 to the left. One big difference between a translation and stretches and reflections is that a translation has no invariant points. Every point is affected equally. In this case, all x coordinates became 4 less, or 4 to the left. Let's try those same two transformations, but in the opposite order. First, we'll apply the horizontal translation and move each point 4 units to the left. Notice that all of the x coordinates were affected, but none of the y coordinates. Now we'll apply a vertical stretch by a factor of 2. As before, our height of -4 became -8, and our heights of -3 became -6. It seems we get the same graph either way. We can conclude here that the order of these transformations does not matter. Why is it, in this case, that a stretch and a translation do not mind the order? Well, remember, a vertical transformation of any kind only affects the y-coordinates, while a horizontal transformation of any kind only affects the x-coordinates. That means that a horizontal transformation has no effect on the range, and a vertical transformation has no effect on the domain. Here, because they were not both affecting the domain or both affecting the range, they did not interact, and therefore their order did not matter. In our next two examples, we'll explore multiple transformations which either both affect the domain or both affect the range. Here, we'll begin with a parabola defined by f of x equals x squared minus 4x plus 3, and we will apply both a vertical stretch, or reflection, and a vertical translation. Let's first apply a vertical stretch by a factor of 2, and then a vertical translation 3 units down. Stretching vertically by a factor of 2 lowers our vertex from 2 and -1 to 2 and -2, and raises the points found at 3 and 3 and 0 and 3 to 3 and 6 and 0 and 6. Of course, our x-intercepts remain invariant because the heights of 0 double and remain 0. Now we'll move all of the points 3 units down. This puts our vertex at 2 and -5. When we look at our mapping rule, we see that xy becomes x and 2y minus 3. Effectively, the transformation of y will follow the order of operations, which is to say, we multiplied y by 2, and then we subtracted 3. We can represent this transformation by writing g of x in terms of f of x, with 2 as an a value in front of f of x, and minus 3 as a k value, representing that translation down 3. To put this in terms of x, simply replace f of x with its expression of x squared minus 4x plus 3. We distribute the 2 through the bracket and subtract 3. This simplifies to g of x equals 2x squared minus 8x plus 3. If you were to graph this in your calculator, you should get the same parabola that we see on the right in green. Now let's try the vertical translation 3 units down first, before the vertical stretch by a factor of 2. After our first step, we see that our vertex of 2 and -1 has become 2 and -4. When we then stretch this by a factor of 2, the -4 doubles to become -8. This mapping rule then follows its order of operations, which is to say we subtracted 3 from the y value first and then multiplied the result by 2. When we simplify this, we get 2y minus 6. Effectively, the translation of 3 was doubled. Writing this in terms of f of x, we would get 2 times the translated f of x, which is to say f of x minus 3, which means that we have 2f of x minus 6. In terms of x, we again replace f of x with its original expression of x squared minus 4x plus 3, and simplify to g of x equals 2x squared minus 8x. Excuse me, h of x equals 2x squared minus 8x. Clearly, we can see these two graphs are different. The reason is not much different than how brackets change the order of operations in any basic expression. When we translate before stretching, the translation is effectively stretched. Now, a note to add to this, we'll often hear about the proper order of transformations, which is to say we should apply stretches and reflections before translations. I'd like to make a clarification. This is referring to situations where we are starting from the base form of any graph, which is to say, when we compare y equals x squared to any parabola written in a form with parameters such as a, b, h, or k. For example, something written in vertex form as y equals 2 x minus 4 squared plus 3. When we talk about those transformations, we want to think of them as though the stretches and reflections happened while the vertex was still on the origin. That is to say, the translations that are written explicitly are the translations we wish to apply. And that wouldn't work if we apply the translations first. All of that to say, stretches and reflections do go before translations when we write in the base form. However, it's not uncommon to find questions where an already transformed graph is now being stretched or reflected. And so if the question is written in an improper order, it is up to you to respond to that and stretch and reflect the given points as they are. Let's walk through another example with multiple transformations acting in the same direction. Here, we will have a radical function f of x equals the square root of x plus 4 minus 1, affected by both a horizontal stretch, or a stretch about the y-axis, by a factor of 1/2, and a horizontal translation, moving the points 4 to the right. After multiplying each x-coordinate by 1/2, we will now add 4 to each x-coordinate to shift the graph right. Our mapping notation shows that xy became 1/2 x plus 4 and y. This respects the order of operations. We multiplied by 1/2, then we added 4. When determining the equation, we'll think less in terms of order of operations and more in terms of order of replacements. We will first replace x with 2x, as the stretch was the first transformation applied. Remember, a b value of 2 means that the stretch factor was 1/2. Now, we will replace x in the same equation with x minus 4. This represents the translation of 4 units to the right. In order to determine the equation in terms of x, we begin with our f of x equals square root of x plus 4 minus 1, and as our first replacement, replace x with 2x. Then, in order to apply our translation, we replace the x with x minus 4. We can now simplify this by multiplying the 2 through to the x and the negative 4, giving us 2x minus 8. And since negative 8 plus 4 gives negative 4, our final form is g of x equals square root of 2x minus 4 minus 1. So what would happen if we applied the same two transformations in the opposite order? First, we add 4 to each x coordinate to move the graph to the right. Now we stretch by a factor of 1/2. Already we see that the two graphs are not the same. Our mapping rule shows us that we would first add 4 to each x coordinate before multiplying by 2. Effectively, this simplifies it to 1/2 x plus 2. The reversal of the order of these transformations means that effectively the translation of 4 units to the right has been stretched by 1/2. To determine the equation for h of x, we will first replace x with x minus 4. Then we will replace x with 2x to represent the horizontal stretch by 1/2. Similarly, in the equation in terms of x, we will first replace x with x minus 4, which we can simplify to give us h of x equals square root of x minus 1. We then replace x with 2x. We can see that these two equations and these two graphs are entirely different. Therefore, when a stretch and a translation occur in the same direction, which is to say both horizontal or both vertical, the order will be relevant. I want to take a minute to explain what this next slide is all about. Here we're going to analyze different transformations, and the point is to show that while functions can be written in different yet equivalent forms, some of those forms do a better job of making explicit or obvious what the transformations are. So here we've given pairs of functions, one base form and one transformed form, to ask if the transformations seem obvious in the given form. And then later, we'll try to rewrite it in a way that might make it a little bit more obvious what's happened. For example, the first pair shows y equals the square root of x paired with y equals the square root of 2x plus 8. And what we're wondering is the translation obvious in that form? Well, we see a plus 8 under the root sign and might think the graph should move 8 to the left. However, what we see is that the blue graph moved 4 units left in order to have the same endpoint as the green graph. This may not have been what you were expecting. In our second graph, we see negative x plus 5 in the bracket, where before there was just x. In previous situations, when we've seen plus 5, that has meant moving 5 units left. But here, we've moved 5 units right. And in our third example, where we have a cubic function, we've replaced the x with negative 1/2 x plus 4, which might make us think that we're moving 4 to the left. But here, we've moved 8 units right, and we've reflected horizontally. All of this is to say that when we want to see what the transformation really is, specifically the translation, we should write our functions in a factored form. And when we think about the general form of y equals a times f of b times x minus h plus k, which is basically saying the function f of x with all of the transformations we've studied in this course, which is to say a as a vertical stretch or reflection, b as a horizontal stretch or reflection, and h and k as our translations, it's only when we factor b out that h becomes more obvious. So the example of y equals the square root of 2x plus 8, if we factor the 2 out of that binomial, we see 2 times x plus 4. And at that point, the x plus 4 tells us, we have translated 4 units to the left rather than 8. Of course, there's also been a horizontal stretch by a factor of 1/2, but that would not have displaced the blue graph originally because its endpoint was on 0, 0. Now, in the second pairing, this can be a little bit confusing because when we factor out that negative sign, we then see the translation of 5 to the right. But the negative sign would represent, in this state, a negative b value or a reflection in the y-axis. However, the blue parabola shown there, if reflected in the y-axis, would not change at all, which is to say that that transformation really has no effect. It might not surprise you then that if we applied our exponent of 2 to both the negative 1, which the negative sign is, in front of the x minus 5, and to the x minus 5 bracket, we could effectively cancel out that negative sign and simply express this as y equals x minus 5 squared, a more accurate representation of the translation of 5 units to the right. Maybe the best way to write this cubic function for our purposes would be to simply factor out the negative 1/2 from the negative 1/2 x plus 4 to show that we have a reflection in the y-axis, a stretch horizontally by a factor of 2 about the y-axis, and a translation of 8 units right. However, for fun, I will show you that if we applied that that exponent of 3 to the coefficient, it would turn into a negative 1/8. Well, there's a fair bit to say about this. In particular, when we write the 1/2 in the earlier step, that is treating it as a horizontal stretch by a factor of 2. When we write it as 1/8, it's now outside of the effect of the power of 3, the exponent of 3, and is therefore an a value. This is representing it more as a vertical stretch by 1/8, which in the case of a cubic are equivalent stretches, horizontally by 2 and vertically by 1/8. Also, as it happens, a reflection in the y-axis and a reflection in the x-axis are equivalent for the base form only of a cubic function. And so, in a weird way, we can see how these two equations, which is to say the y equals a bracketed negative 1/2 bracket x minus 8 close 2 brackets to the 3, is the same as y equals negative 1/8 times x minus 8 cubed. But for the purpose of this slide, the earlier form with the negative 1/2 would have been more helpful to just stop there and to identify our stretch of horizontal stretch by a factor of 2. In class example 1.41, we will apply 4 transformations to a given graph. Here, we'll take y equals f of x and transform it into g of x, which is defined as 1/2 of f times negative x plus 2 plus 1. The question first asks us to construct a mapping rule. And even if it hadn't, this is a great way to approach this question. Transforming a graph with 4 separate transformations one at a time can be a little bit cumbersome and often leads to small errors. Let's see how the mapping rule will help us. First, we want to prep our function by factoring out that b value. Because we had a negative in front of the x, we'll take out negative 1 from the bracket, which will change it to negative times x minus 2. This means we have a vertical stretch by 1/2, a reflection in the y-axis, a shift of 2 to the right, and 1 up. In mapping notation, we'll represent this by showing that our x value became negative, and was increased by 2, while our y value was multiplied by 1/2 and increased by 1. This mapping notation allows us to take any point and substitute it in place of x and y and determine the coordinates of its transformed point. So, if we take negative 7 and multiply by negative 1 and then add 2, And if we take negative 5, multiply it by 1/2 and add 1, we find that our transformed point would be 9 and negative 1.5. This is easier than drawing the same graph 4 times after each transformation. Now that we have transformed all of our points, we can sketch the graph. Next, we're told that the point P, whose coordinates are 0 and 2, lies on the graph of f of x. In order to find its coordinates on the graph of g of x, we will use the exact same process, substituting into our mapping notation. Here we determine that the point 0 and 2 transforms to 2 and 2. Given that we've already drawn the graph, we can identify that the domain of the transformed graph is from the leftmost point of negative 7 to the rightmost point of 9. And the range is from the lowest point of negative 1.5 to the highest point of 3. Class example 1.42 is a wonderfully challenging question, which is rather conceptual. The reason for this is we're asked to work on the function y equals f of x, but we're only given a domain and range. We're not given an equation in terms of x, and we're not given a graph. However, I bet that you could sketch a graph that satisfied a domain of negative 4 to infinity and a range of negative infinity to 9. Take a moment to do so before proceeding with the question. Now, we're asked to provide a mapping rule for a transform function described by y equals negative 1/3 f of 2x. And then using this, we will determine the new domain and range. We know that an a value of negative 1/3 means a reflection in the x-axis and a vertical stretch, or a stretch about the x-axis, by 1/3. A b value of 2, that coefficient in front of the x, represents a horizontal stretch factor, or a stretch about the y-axis, by a factor of 1/2. So we write that all points x, y become 1/2 x and negative 1/3 y. Let's get back to that sketch of yours. I drew a partial parabola with an endpoint at negative 4 and 9. In order to visualize this after, I applied the mapping rule to the endpoint. This gave me a new endpoint of negative 2 and negative 3. But be careful, while the x value was only stretched, the y value was stretched and reflected. Well, if that point was reflected, so was the entire range, which is to say the entire graph is now going to open up instead of down. This will affect whether our values are minima or maxima when writing the domain and range. So for our domain, the negative 4 that became the negative 2 is still the minimum value of the domain. However, the positive 9 that became a negative 3 has changed from being the maximum value of the range to being the minimum value of the range. Let's now look at part B, which again has multiple transformations. One of the first things you'll want to do if given a transformed equation is make sure that it is rewritten or properly written in the format that makes most obvious to you what the parameter values are. Here, because it originally said y plus 5 on the left side, the k value had a sign, a positive sign instead of a negative sign, which we're not accustomed to seeing. Also, within the bracket, we saw a negative x plus 1. We need to factor that negative 1 out as a b value in order to make the h value, or horizontal translation value and direction, more explicit. From here, we can write our mapping rule. We see that x has been affected in two ways. There's a reflection in the y-axis and a translation of 1 unit right. Our y value has been affected in two ways, a vertical stretch by a factor of 2 and a translation of 5 units down. Much like the last example, we'll apply this mapping rule to our endpoint of -4 and 9. This time, our new endpoint is at 5 and 13. Much like our last example, our graph has undergone a reflection. However, this time, a horizontal one. That means that the domain will change from having a minimum value to having a maximum value. As we can see, our new domain is from -infinity up to 5, and our new range is from -infinity up to 13. In class example 1.43, we will apply multiple transformations to the graph and equation of an absolute value function. So here, we're given f of x equals the absolute value of x minus 6 minus 4. Basically, an absolute value function that has been shifted 6 right and 4 down off of the origin. We're then given g of x, the transformed function defined by -f of 3x minus 6 plus 3. In our first step, we're asked to construct a mapping rule for the transformations from f of x to g of x. And we want to be very, very aware of the fact that that 3 in front of the 3x has not been factored out. This is easy to miss, but is so important. As long as the b value is not written in factored form, the h value, or horizontal translation value, is not correct. By factoring that 3 out, we can write 3 times x minus 2 and know that we'll be shifting 2 units to the right. Now, our other transformations are a reflection in the x-axis, a horizontal stretch by a factor of 1/3, the shift 2 to the right, and then a translation of 3 up. Our mapping rule, therefore, will show, due to the vertical reflection, that y becomes -y. Because of the horizontal stretch factor, that x has a coefficient of 1/3. And because we move 2 right, we will add 2 to the x value, and 3 up will add 3 to the y value. Let's transform each point on the graph that is indicated using our mapping rule. In the end, we see a reflected, stretched, and translated absolute value function. Now we'll find the equation for g of x in terms of x. This means taking the original equation and applying the transformations to them. Let's first apply all vertical transformations. It's important here that we apply the reflection prior to the translation of 3 units up. You'll notice, therefore, that we've bracketed the absolute value x minus 6 minus 4, multiplying it by a -1 before adding our 3. Now we will apply our horizontal transformations. This requires us to replace first the x with 3x and then the x with x minus 2. Or in one step, we can simply replace x with the 3x minus 6 that was originally shown in the non-factored version. The result will be the same. As we simplify what is inside the absolute value brackets, we get 3x minus 12. As we distribute the negative sign both in front of the absolute value brackets and to the -4, we get a plus 4, which adds to the 3 to give us a 7. We can confirm using our graphing calculator that this form in terms of x will generate the same graph we've seen that we drew above. Class example 1.44 asks us to determine the equation of a transformed function. This is often rather difficult because it asks us to work with transformations in unconventional orders, which is to say we're transforming an already transformed graph or function that may have been translated and now we're stretching it or reflecting it. But if we take a step-by-step approach and use a graphical confirmation, we should feel quite confident in our answers. Let's start by looking at the function f of x equals 3 times the square root of 6x plus 1 after we transform it with a vertical stretch by a factor of 4 and a vertical translation 6 units up. Writing this in terms of f of x, we see that the vertical stretch by a factor of 4 would give us a coefficient of 4. And a translation 6 units up would give us a constant term of 6. If we now want to determine our equation in terms of x, we simply replace f of x with its corresponding expression of 3 root 6x plus 1. If we multiply this by 4 and add 6, we will get a simplified equation that corresponds to our transformed function g of x. Now, how can we use our graphing calculator to confirm this answer? We'll start by graphing f of x and g of x on the same graph. You'll notice we've adjusted the window settings. You may have to play around with this, but for now, just use the ones we've presented for you. Because both of our transformations were vertical ones, both the stretch and the translation, any 2 points with the same x-coordinate will be corresponding points. For example, if we determine the value of both of the y-intercepts, we would see that 0 and 1 has mapped to 0 and 10. We can confirm this in our mapping rule, where xy becomes x and 4y plus 6. If we replace x and y with 0 and 1, we see that the point 0, 1 maps to 0 and 10. We don't need to limit ourselves to only the y-intercept in this case. We could also check the point, for example, 6 and 19. Under our mapping rule, we will see that it maps to the points 6 and 82. Confirming that these 2 points appear on our transformed graph is probably reasonable confirmation that we have correctly determined the transformed function. The second part of class example 1.44 becomes a little bit more complicated because now we will work with vertical transformations and horizontal transformations at the same time. Here, we have a reflection in the x-axis. That's a vertical reflection. We have a stretch about the y-axis, which is a horizontal stretch, by a factor of 1/2, and then we translate 3 right. The reflection in the x-axis shows up as a coefficient in front of f of -1. That's the a value. The horizontal stretch by a factor of 1/2 shows up as a b value of 2. And then our translation of 3 units to the right shows up as x minus 3. Because the stretch happened first, the x minus 3 will be bracketed. In order to work on our equation in terms of x, we're going to be a little bit inconsistent here, and I'll address that in a minute. First, I will treat the vertical reflection as we treated our transformations in the previous example. That is to say, I replace f of x with its corresponding expression of 3 root 6x plus 1, and then apply the transformation, which in this case is a negative coefficient. Note that because we've bracketed the expression, that negative sign will multiply to the 3 root 6x, and also to the positive 1. Dealing with horizontal transformations is a bit trickier though. Really the only option is to write them as replacements. So here, because in the expression, that first line, instead of having f of x, we had f of 2 times x minus 3, we will here replace the x with 2 times x minus 3. This might make our equation look a little bit clunky, but I do believe this is the most effective way to determine the equation of transformed functions. We can simplify by multiplying the 6 by 2 to make 12, and then the 12 by both the x and the negative 3 to make negative 36. Notice that that negative coefficient has now multiplied to both the 3 and the positive 1. We can also leave the radicand in a factored form, which is to say 12 times x minus 3, which is somewhat more appropriate if we're wanting to graph it. So let's go ahead and graph f of x against h of x. Here, because we have both horizontal and vertical transformations, we won't just look at points with the same x value, but it might make sense to track the end point. Our mapping rule shows that because we stretched by 1/2 and moved 3 to the right, and because we had a vertical reflection, all points x, y become 1/2 x plus 3 and negative y. Transforming the point 0 and 1, we find our new vertex or endpoint of 3 and negative 1. While they may not be as obvious to follow, we can also take another point, such as 6 and 19, and map it to find that it gives us 6 and negative 19, and confirm using a table of values that both of these points lie on our two graphs. Hopefully that helps clear up a little bit about how you can deal with vertical and horizontal transformations on equations. Class example 1.45, determining transformations from a graph. Here, we're given pairs of graphs and asked to write the transform graph in terms of the original f of x. This can be a really tough question because often we don't know where to start. But if we inspect the graph for the various transformations, we should be able to determine which have and have not taken place. Let's start by analyzing the height of f of x, which is to say, what's the vertical distance between the highest point and the lowest point? Here we can see its lowest point is -5 and its highest point is 4, so it has a height of 9. While the transformed graph g of x goes from -10 to +8. It has a height of 8. Most of you can probably determine that in order to transform 9 into 8, you have to multiply by 2. This means we have a vertical stretch factor of 2. Next, let's consider the width. F of x goes from -9 to +6. That's a width of 15. G of x goes from -2 to +3 and has a width of 5. To change from a width of 15 to 5, you would have to divide by 3. However, when we talk about stretch factors, we always talk about what we would multiply by. So dividing by 3 is like multiplying by 1/3, which is therefore our horizontal stretch factor. Now we want to know, were there any reflections? Well, both graphs open up, and both graphs have their highest point to the left and, in fact, lowest point to the left. This means we see no vertical reflections and no horizontal reflections. Were there any translations? Well, we have to be very, very careful here. Often students will look at the vertex or lowest point maybe of the graph and will follow it and say, it has moved over and it has moved down. But recall that when we perform a stretch, that will move all points that are not on the stretch axis for the graph. So it may be that the stretches already take care of that, quote, movement. Let's follow the point -9 and 4. As we stretch it by 1/3, we see that it ends at -3 and 4. The point 6 and 0, stretched by 1/3, ends at 2 and 0. In order for our endpoints to align horizontally, we will need to shift our graph one space to the right. When we stretch graph vertically, all of the heights will be doubled. The point that was originally 9 and 4 that became 3 and 4, and then, -9 and 4 that became -3 and 4 that became -2 and 4 would stretch to become -2 and 8. And the point which was last on 0 and -5 would stretch to 0 and -10. We see with this that no vertical shift would be required. The vertical stretch would take care of the shifting of the graph that we needed. We can confirm then that the mapping rule would be x and y become 1/3 x plus 1, and that y becomes 2y. Recall that a vertical stretch of 2 shows up as a coefficient of 2 in front of f, whereas a horizontal stretch of 1/3 shows up as a coefficient of 3. Our translation is written as x minus 1 as we're moving 1 unit to the right. Now that you've followed the example in the first part of 1.45, maybe try the second on your own before clicking through the animations. Here, we will again start by determining the height of both the original and transformed graph. We find that the height of f of x goes from -9 to +9, so it is a height of 18. G of x goes from -6 to +6. This is a height of 12. This allows us to determine that our vertical stretch factor must have been 2/3. Next, we analyze the width of both f of x and g of x. We find that in both cases, the width is 14. This means no horizontal stretching has occurred. We notice that the orientation of the graph suggests there's been a horizontal reflection. However, because both graphs open up, there's been no vertical reflection. After we apply our horizontal reflection, remember there was no horizontal stretch, is a horizontal shift required for our two graphs to align in position? We can see that the leftmost and rightmost point of our reflection require a shift of 2 units left. Once we apply our vertical stretch by a factor of 2/3, we will see that there's no need for a vertical shift. The points will align. We can conclude then that our mapping rule is xy becomes -x, the reflection in the y-axis, minus 2, shifting left, and that y becomes 2/3 y. That's our vertical stretch by a factor of 2/3. In our equation then, we would see our stretches and reflections represented with a 2/3 coefficient in front of f and a negative coefficient in front of x. And because we want to go 2 units to the left, we replace x with a bracketed x plus 2. These are tricky questions. If you manage to find that on your own, congratulations. The only thing more fun than math is more math. We thought we'd give you one bonus example here. We are going to determine the equation of a transformed function. Now, this example is not in your workbook, so don't panic. But we thought we'd work with something a little bit familiar, like a parabola, and then load it up with transformations and see if we could find the equation in terms of x. You might want to stop this video right now and see if you can find it on your own first. So f of x is described as, or defined as, 2 times x plus 1 squared minus 3. We are going to construct a transform function by stretching vertically about the x-axis by a factor of 6, reflecting in the y-axis, translating 4 units right and 5 units down. We'll start by writing this as a mapping rule. Our vertical stretch by a factor of 6, our reflection in the y-axis, the negative sign, our shift 4 right and 5 down. Now, in order to write this in terms of f of x, we need to determine our parameters. The vertical stretch gives us a coefficient of 6. We will subtract 5 at the end outside of the brackets because of our translation. Our reflection replaces x with negative x, and then our translation 4 right replaces x with x minus 4. So, let's see our equation in terms of x. It's important that we apply stretches before translations within each direction, which is to say, it's okay to apply a vertical translation before a horizontal stretch, but not a vertical translation before a vertical stretch. So the first thing I'll do is I'll multiply my entire original function by 6. This is the vertical stretch of 6. Then I'll subtract 5. In order to represent our two horizontal transformations, we'll be replacing x with the negative x minus 4. This gives us g of x equal to 6 times 2 bracket negative x minus 4 plus 1 squared, subtract 3, minus 5. Wow. Let's clean this up a little. The 6 out front distributes to both the 2 and that negative 3. That takes care of the square brackets. Within the circular brackets, the inside brackets will distribute the negative sign to both the x and the negative 4. At this point, it's probably easier to follow, but we've added the 4 and the 1 to make the 5, and we've added the negative 18 and the negative 5 to make the negative 23. Now I'm going to divide out the negative sign in front of the x, which makes it negative 1 times x minus 5, and I apply the exponent of 2 to both of those factors. Because the negative sign is really negative 1, its squares become a positive 1, leaving us with 12 times x minus 5 squared minus 23. So how do we go about verifying such a complicated question? Well, we do have the equation of the original function, and we do have the equation of the transform function, and we do have a graphing calculator. Let's go ahead and graph f of x and g of x. We'll need to adjust our window a little bit, as g of x has its vertex as low as negative 23. Whether we use the equations, which are in vertex form, or we use the second calc minimum function of our calculator, we can determine our vertices here to be negative 1, negative 3, and 5 and negative 23. Let's see if the vertex at -1 and -3 lands on 5 and -23 using our mapping rule. We replace x and y with -1, -3, and are happy to find our anticipated result. This strategy of using your graphing calculator to check your answers can really increase your confidence, much more than flipping to a back answer page. Knowing that you got it on your own and that it is correct can make you feel great. This is a tough question. If you got this, well done.